21 review, and you notice we did skip D&E. We're not doing D&E. Review number 1. A survey organization draws a simple random sample of 1,000 registered voters in a certain town. In the sample, 32 approve of the mayor, 32% approve of the mayor. The organization estimates that 32% of all 50,000 registered voters in the town approve of the mayor. How do they figure the SE? The organization realizes that the number in the sample who approve, blank, 1,000, draws, blank, blocks, blank. Using 33 words or less. So the organization realizes that the number in the sample who approve what? (32% of 1,000), good. Of 1,000 draws. What did you guys come up with? So we have about 50,000 people in the box. That's probably not even correct. So we take a sample and we get 32% approve. That is a sample of 1,000. So the organization estimates that 32% of all 50,000 registered voters in the town approve of the mayor. How do we figure the SE? Well, the organization realizes that the number in the sample who approve of the mayor are 32% of 1,000 draws from the box 0.32, 0.68. Right? We don't know what's in there, so we put in 0.32, 0.68. And then we find the SE. Well, as long as it's SEP, it's really easy to find. Square root of 0.32 times 0.68, and we're going to divide that by the square root of 1,000. So our answer is 32 plus or minus 1.5. Now, they worded that really weird, but something to that effect. Number 2, the Residential Energy Consumption Survey found in 2001 that 47% of American households had internet access. A market survey organization repeated this study in a certain town with 25,000 households using a simple random sample of 500 households. 239 of the sample households had internet access. So we have 2 different groups. One we know was 47%. We don't know how many people they talked to. And then later, the sample was repeated with 500 people, and we ended up with 239. The percentage of households in the town with internet access is estimated at whatever 239 divided by 500 is 47.8%. The estimate is likely to be off by the square root of 0.487 times whatever 1 minus 0.487 is. And then we have to divide that by the square root of 500. Now, before I push enter, does everybody understand that calculation? We use the SD shortcut because it's a 0, 1 box. So we don't even do 1 minus 0 anymore. So it's just the square root of the yeses times the no's divided by the square root of the number of draws. So 47.8% plus or minus 2.2%. If possible, find a 95% confidence interval for the percentage of all 25,000 households with internet access. So 95% confidence interval is just 2 SEs. So we're going to add 4.4. So we take 47.8 plus 4.4 and maybe and 47.8 minus 4.4. So technically you can write it like this, 47.8 plus or minus 4.4, but it's a little bit more descriptive if you just say from 43.4 to 52.2. And that's the way we want to write our confidence intervals. 43.4 to 52.2. You can't read my handwriting? So I am 95% confident that the true percentage is somewhere inside 43.4 and 52.2. Now, can I figure out what the 95% confidence interval for people in the entire country is? No. Why not? So, right. So I was told the whole country is supposed one sample of the country had 47%. The sample from this town had 47.8%. So I created a confidence interval. Can I create a confidence interval for the entire country if I know that a sample was 47%? No, I'm missing something. There's just one number I don't have. I don't need to know how big the population is. I need to know how big the sample was. So the original sample said 47%. I don't know how big that sample was. Do you ever hear a statistic on the radio or see it on Facebook or somewhere else, and they say 48% of Americans fill in the blank? And you just say, oh, wow, that's nice. Is that a statistic or a parameter? It's probably a statistic. If they didn't ask you, then it had to have been a sample, right? So what does that 47% mean? Who knows? You don't know how they did the sample. You don't know how big the sample was. And without the sample size, you don't know the standard error. And without the standard error, you can't figure out the confidence interval. So a good statistical reporting entity will say that this 47% is expected to have a 2.5% error. But even then, you're not sure if it's a 95% confidence interval. Is that 2.5% one standard error? Is it two standard errors? Is it three? Because it could be three. So news agencies are terrible at statistics. They just don't understand them to the point. And granted, it took you guys 6 months to get here, right? I can't run around and teach everybody how to do this because it took us 6 months before we could start learning about statistics. Well, 18% of all statistics are made up on the spot. Yeah. Every time I tell that joke, it's a different percentage. Okay. You guys are doing well. Number 4. Wait, we didn't do 3, but we're doing 4? That's cruel. I didn't pick these problems. The university did. So 500 people, 121 had no car, 171 had one car, and 207 had 2 or more cars. Estimate the percentage of households in the town with 1 or more cars. So that would be 172 plus 207 is 379. I guess we didn't need to do the previous problem, right? So 379 out of 500. So 75.8. So I take the square root of 0.758 times 1 minus 0.758. And then I'm going to divide that by the square root of the number of draws. So we expect 75.8 plus or minus 1.9 percentage points. Okay. It is possible. So we're going to say we are 95% confident that the actual percentage is 75.8 minus 3.8, 72, and then 75.8 plus 3.8, and 79.6. So if I told you 75.8% of people have one or more cars, you should have a lot of questions for me. And I said, okay, fine, I'll give you more information. 75.8, I have an error of just about 2%. And you have to say, well, is that the standard error? Or is that the 2 standard error? What do you mean by that? Are you 95% confident that the standard, it's plus or minus 3.8? So anyway, lots of information that you should be asking. And it turns out most research organizations know what they're doing. Well, so I was involved in some research projects at BYU. They have this program where they take undergraduate students and they actually paid me to be a research helper. And now granted, they were all math ed research things, so they pretty much understood statistics, but still, one day in one of our projects, we went and visited the statistics department as a team, and we sat down with them and said, this is how we plan to conduct our study. And these 2 statistics professors said, okay, well, you need to understand this, and you need to understand this, and you need to understand this. So even if researchers don't understand statistics, they usually consult a statistician. But the only trouble is, researchers write really, really boring papers. And reading the papers is sometimes gouge your eyes out awful. So what reporters do is read the summary. And then they pick the stuff out of the summary that they think they understand, and then they plaster it all over the internet. So you're better off going to the study. Most of them are quite good. Okay, now 11. 100 draws will be made at random with replacement from a large box of number tickets. There are 2 options. To win $1 if the sum of the draws is bigger than 7710, and to win $1 if the average of the draws is bigger than 7.1. So 100 draws will be made at random without replacement from a large box of number tickets. There are 2 options. If the sum is bigger than 710, you win $1. If the average is bigger than 7.1, you win $1. What do you think? Well, what's in the box? Just numbers. We don't know what they are. Okay. What is the difference between the sum of the box, as far as calculations are concerned, and the average of the box? How do you calculate the sum of the draws? You add up all the draws. How do you compute the average of the draws in this case? Add them all up and divide by 100. So is there any difference between 710 as a sum and 7.1 as an average? No. The only difference is the sum is just adding them all up, and the average is dividing by 100. So the probabilities of both will be the same. Okay. Awesome.